So we have our first ranking problem. In this problem we have a power plant that contains a turbine, and that turbine produces 1750 kilowatts of power. The two pressures that this cycle operates within is 6 megapascal in the boiler and 20 gigapascal in the condenser, with steam entering the turbine at 500 Celsius. We are requested to find heat supply, heat reject, and the efficiency of the boiler. So we're gonna solve this problem step by step, and here we go. We're gonna start by drawing our process in a TS diagram, and we are also gonna draw the components of the cycle. So first of all, in the TS diagram we draw the dome, as you can see it, and then in black you can see the two pressures between which this cycle will operate. The lower pressure, which is the condenser pressure, will be the lowest, and the boiler pressure, which will be the highest. So we introduce our turbine and now our pump, and we mark our states 1 from the pump, 2 the entrance of the boiler, 3 the entrance of the turbine, and 4 the entrance of the condenser. So we will have 2, 3, 4. And here we just check the pressures. It's 6 megapascal and 20 kilopascal for the boiler. If you are not sure about the numbers, it's always a good practice to go back to the problem and see how it's defined. So we are just checking now the temperature, which is 500 degrees. We create a dotted line here just to make sure that we remember that this is 500 degrees. If you cannot read it, it's 500. So now we are drawing all the components, and they're just showing how they are connected, and we're identifying the proper relations and the states. So here we just draw the turbine and showing that it has some work turbine out, the pump showing that we have work in. This is state 2 because it's the of the pump. 1 will be the inlet, state 3 at the outlet of the boiler, and state 4 at the outlet of the turbine. And we write all pertinent information like the power that this turbine is delivering. It's not the complete plant, it's just the turbine. Now we are defining how are these states, and we know that since this is an ideal cycle, a basic ideal cycle, we have saturated liquid at the entrance of the pump. So we indicate that quality of 0, that means no mass in form of vapor, and the pressure is 20 kilopascal. Remember that we need two independent properties. For state 2, we know that is state 1 plus the work of the pump. We are assuming an isentropic pump, and the work of the pump can be approximated as the volume of the fluid, which could be 1 since it's incompressible, plus times the pressure difference. State 3 is so easy to define because it's a superheated vapor, 6 megapascal and 500 degrees. So here we are indicating it is superheated. State 4, we know that state process 3 to 4 is an isentropic turbine. So one of the properties that we are going to need, we already know it, is 20 kilopascal, the pressure at the outlet of the turbine. And the other property, since it's an isentropic process, we are going to consider it to be the entropy. Entropy is the same as entropy 4, and these two values define the state. So we go back and check what we were requested to find, and we read that this heat supply, heat rejection, and efficiency. So we're just going to point it out so we know what we are looking for. Looking heat rate in, heat rate out, and it's rate, so don't forget the dot. That dot means per unit time. And so we are just making the note that we are looking for rate, so that's why we're using this dot. And the efficiency, remember that we define as the network of the plan divided by the Q in is what we want divided by what we need to invest. This work net, we can find it two different ways. One way will be subtracting the work pump to the turbine work. The other one will be just by using first law, the difference of Q in minus Q out. Remember that is the area inside the curve. Here's what we first said. So we have these two ways of finding it. We know that we can get all the properties above, so the problem should be very straightforward to solve. Since Q in is the mass flow rate times the enthalpy difference, that is H3 minus H2, we notice that we need mass flow rate, and we wonder where we can get it from. But we remember that we have the power of the turbine to be the mass flow rate times the enthalpy difference, and this is equal to 1750 kilowatts. So basically we can solve for the mass flow rate and find out that mass flow rate will be the power of the turbine divided by the enthalpy difference. Here we show we're solving for mass flow rate. It's again the power of the turbine, which we know, divided by the enthalpy difference, which we can find out. So basically what we need is to find out the four states, H1, H2, H3, and H4, just as we defined it. So let's start. First of all, we're going to use tables. These tables are in your blackboard. They are under course materials, and you have an updated copy of the temperatures in the back of your book. So we are going to find properties as we mentioned in tables A4, A5, and A6. A5 and A6 in this problem, since we're going to use pressure to enter the properties. We know two pressures. So for state 1, we know that pressure is 20 kilopascal. We look for here, and you see that 20 kilopascal we have different properties. We copy volume 1, which we are going to need it for the work of the pump, and enthalpy 1, which is the energy at the end, at the inlet. Try not to use your memory. If you in doubt, just go back and copy the right value. So this is state 1. So now we'll go for state 2. State 2, we know that we have the pump as we described, so we only find it by finding out the pump work, which will be this volume, specific volume 1 that we just found, 0.001017 times the pressure difference. Please take care that the pressure of the boiler is 6 megapascal and the pressure of the condenser is 20 kilopascal. Both should be in the same unit, so 6 megapascal is converted to kilopascal, so it will be 6,000. And this work will be close to 6 kilowatts, kilojoules per kilogram, sorry. So if you compare that number with the energy that goes inside the pump, you can see that it is small in comparison, and that's why sometimes work of the pump is neglected. Obviously, if we have only pumps, this cannot be the case, and you need to consider it because this work needs to be gathered from somewhere, and usually you use part of the turbine work to drive the pump. So as we said, it's near 6.08, and the temperature will be, the total enthalpy 2 will be 257. Please remember that we are considering an isentropic pump. If we have a real pump, we're going to introduce in the next part isentropic efficiency. So now for state 3, we remember that it is superheated vapor. And here we are just stressing out that this is the work pump. So for state 3, recall this is superheated vapor. So we need two properties. Property will be 6 megapascal and 500 degrees. And we're going to find this data in table A6 instead of table A. In this table we needed two properties. The properties that are listed here are pressure and temperature, but we can get any combination of two. For this problem we're going to use pressure, which is 6 megapascal. We can assume here, so it's 30 megapascal. Sorry, 6 megapascal and 500 degrees. So these are the values of volume, internal energy, enthalpy, and entropy. So we copy our values, and we know that H3 is 3,412.3 kilojoule, 0.1, 4,412, 23.1, and 6.882 for the entropy. And we're going to need this to find out state 4. We are going to do it in the next page so we don't have a sloppy solution, and I encourage that also for your homework and for your exam. Neat solution is easier to grade, but it's also easier for you to find out when you commit a mistake. So for stage 4 we need two properties. The first one is pressure, we know it's 20 kilopascal. Second one is entropy. And in order to find out what kind of vapor do we have, we compare the entropy 4 with the saturated vapor and entropy at 20 kilopascal. Since the entropy, saturated vapor entropy is bigger, 7.9 versus 6.8, we know that we are inside the dome. So we need to compute quality, and quality we are computing it by doing S4 times S4 minus SF divided by the SFG. So this is in general the way we are going to find out quality. We make this calculation and we find out that quality is, here we are watching, see how we are stressing the numbers that we are finding out. This SF, SFG, and SG. SF is the saturated fluid, SG, saturated vapor, SFG is the difference between these two. So by doing the math, we find out that is 8.85. Recall that quality should go from 0 to 1. 0 meaning saturated liquid, 1 saturated vapor. In between will be that the amount of mass that we have, the percentage of mass that we have in form of vapor. With this we can get our H4, and we are just substituting the value of quality 4 in the enthalpy expression. And we have 2267.5. This number is the enthalpy leaving the turbine after we expand it. So now we have all the data we need. We have the 4 enthalpies. We're going to compute the mass flow rate. We'll call this the power of the turbine divided by the specific work of the turbine. So it's 1750 divided by H2 minus H4 minus H3 minus H4, sorry, H3 is the inlet, H minus H4. So this gives us our mass flow rate. We do the math. And we have that it's 1.51 for 4 kilograms per second. And we just highlight that in this current too. This is an important result, so we are just highlighting it. With the mass flow rate, we can easily find out the heat addition rate and the heat removal rate. Heat addition will be the same mass flow rate times H3 minus H2. Remember that this H3 minus H2 comes from first law analysis of a steady state boiler that we described in the previous video. So we already derived this formula, so it's 1.44 times the enthalpy difference, 3423.4 is the enthalpy at the end of the boiler, 257 is the entropy at the inlet, so the difference is the total amount of heat that we add per unit mass. Multiplied by the mass flow rate, we had 4,794. We do the same for the heat rejection, and we can get our value. In this case will be the heat that is being rejected in the condenser. Here we go. Sorry. So we have 3053.16, and the units of this two are kilojoules per second or kilowatts. We should never forget to put it, and I'm doing that right now, but we should do it in both places. And finally, we are computing the efficiency. And the efficiency, we can use both the rate form or the specific form. Since we already computed the rate form, we are going to use that value. Basically, we have 0.3630, and if we express it in terms of efficiency, I mean in percent, we just multiply times 100, and we are gonna get it. So efficiency for this cycle is 36.3%. Well, with this we complete our problem. It's a long video, it's 20 minutes. It's longer than I expected, but it's a detail, and you can go back and check everything. Thank you very much for your attention. One thing that I would like to stress is that you will not learn just by watching the video. Take notes, repeat the video at your computer. Following video on another ranking problem, and finally with reheat. Well, that's it, guys. Thank you.